Okay. Welcome to the Astronomy Club meeting. First note, as some of you may know, Rodrigo, a member of our club, was able to get us 36 by 48 kind of stand-up poster, really nice display, and Katie made this nice, cool picture about our club, and so that's going to go places that we go now, so we can show off how cool we are. Anyone who has signed up or is going to do the Vale Academy Boxer Expo this Saturday, please meet with this Friday. Yeah, please meet with Katie so you can sort out schedule stuff and everything that you're doing. One thing that we're going to do, I remember I told you guys about Camp Wildcat a few weeks ago, a little bit more than a few weeks ago, and they had a camp that we were asked to do a star party for. Unfortunately, it was the first Saturday of the month, and we couldn't really schedule anything around it. But they have other camps, and so the April 16th, which is not this Saturday, but next Saturday, they want us to help them do a star party, and it'll be just here on campus, starting at 7:30, and just kind of going till it stops. And as they say, it's a non-profit organization that helps the Tucson youth see college as something to try to do, and it'd be nice to really show off our astronomy, the astronomy that we have here. And if you want to participate, I'm sending around a sign-up sheet. I think most of you know about our projects. One added note, we made sure that you know that the binocular telescope project meets Thursdays at 5 p.m. That's when we're going to start working on that, and hopefully soon that will really get rolling as we get mirrors and secondaries and really finalize designs. Astronomy question of the week. Come on, guys. It's lots of fun.
Last time we discussed that you're as popular
Yes.
as your friends.
Probably you aren't as popular as your friends are. And if you want to know why, you can come to the astronomy question of the week. You can learn all about that. One thing that's happening this weekend is the Arizona Space Grant Consortium meeting, and a lot of people will be gone this Friday and Saturday to go present our research. And so I just kind of wanted to say a word about Space Grant and what it is. It is an opportunity that NASA provides. It's in that the federal government allocates certain, you can become a land grant university or a sea grant university, but you can also become a space grant university, which means you just get lots of money to research land or oceans or space. And we're a space grant university, and it's really one of the best space grant programs in the country. And so you can apply to this program, and if you get in, then you get paid to do research, and they set you up with an advisor, and they have all kinds of programs throughout the year that help you do your research. And at the end of the year, or at about this time of the year, you present your research to other people throughout the in the program, in the Arizona program, and just kind of show how successful it is. This is kind of a list of alumni and where they went after their space grant internship was over, and you can see that it's you got NASA missions, you got PhDs and all kinds of stuff, and so it's really set up for success, and so you should apply. And the application is really easy. It's due July 8th, I think, or sometime in July, and you should apply because it's a great research opportunity. Okay, got back to that. One more thing that I mentioned, if you want to just have a relatively fun, easy class next semester, Physics 399 is Physics Outreach, and basically it's you go to Flandreau every Friday-ish, and you help teach kids about science through fun demonstrations like static electricity as shown here. And it is a 3-credit class, one credit class.
But it can be more depending on what level of involvement you have.
And if you want to know more about that, talk to Kevin because he's taking it now and he can answer all your questions. That's it for the main presentation. And as I said in the email, Kevin and I are going to present our space grant research to kind of show you some research and what you can do in space grant. And I brought this Hoberman sphere as a demonstration of fun physics demonstrations. So my research was talking about using high-precision stellar observations to confirm the physics of convection in stars. So we're going to get a little bit more into that. So first of all, what we're going to talk about. First, I'm going to talk about the current description of convection, which is called mixing link theory. And this is applicable to pretty much any situation of convection, not just in stars. The common analogy is water boiling in a pot. It is very analogous to pretty much any convection that you see in the natural world. And then I'm going to talk about the addition of this geometric parameter, which we hope to more accurately describe convection and have a better understanding of the physics of convection. And I'm going to talk about how we model stars and how we're using this to really test this geometric parameter and look for some trends and fitting some observed stars that it's going to mention the high precision observation part. So first, basically, overview of mixing link theory, the theory of convection. First, we consider like a little blob of material that's just sitting in this huge stellar atmosphere. And for some reason, this little blob of material can kind of become self-contained and become a little bit hotter than its surroundings, just because of random temperature fluctuations. Now, because if you guys know the ideal gas law, then any material that's at constant pressure that becomes hotter, that means it's less dense. And then from Archimedes' principle, it starts to float, just like water bubbles that have heated up in a pot of water float to the top of of the pots because they're less dense than the surrounding water. But as it's floating the top of this kind of column of gas, it's radiating, it's transporting its heat to these upper layers because it's hotter than its surroundings and it wants to be in equilibrium with its surroundings. So it does that through radiation and turbulent mixing. Mixing with the rest of the gas, and after a certain length, called the mixing length, the material will become completely mixed in with the surrounding material, and it has transferred some of the heat from the bottom layer to the top layer. So you could see that I kind of demonstrated that here. It wasn't as hot in the top, but after the blob transferred material, it got a little hotter in the top, and that's showing how it's transporting heat. Now, we can talk about the geometric parameter. Basically, the idea is how efficiently this process of convection works depends on the surface area to volume ratio of these kind of self-contained blobs that float the surface. And normally, they're, in the current formalism of mixing length theory, they're just assumed to be spheres. And as we all know, lots of things that are in the real world aren't actually spheres, but probably have a little bit more surface area, like wrinkling effects and stuff like that. And as you can see, the greater surface area leads to more efficient heat dissipation because there's more surface area to transfer the heat. The way we test the physics of stars is through stellar evolution code. We use the MESA evolution code, which is you can read about it in the technical paper. Basically, given the initial conditions and the description of physics that you want to include, you can completely describe a star's life based on those initial conditions and those physics. You can see here, here if we vary the mass, it can accurately tell you kind of what's happening with its life on the HR diagram, or this is what happens if you vary that mixing length parameter, which is still a free parameter in the way we describe stellar convection. Values vary from 1 to 4 pretty wildly based on who you talk to, and so you can see varying mixing length causes different observations. And the good thing about stellar evolution programs is you can look inside the star, which you can't do in just observations of stars. Now to the other part of the title, I talked about high precision stellar observations. This paper released by Torres et al. Compiled, I think, 128 different stars and binary systems, and they observed transits. They observed a lot of transits to really accurately pin down the mass. They also pin down the other stellar parameters pretty well, so that you can be on the 1% level, which is really amazing for a massive star. And so this can help us really, when we have these initial conditions at this high of a precision, we can really look at how the different physics affects what we see, and we can compare it to the other observations, compare the observations to our model. And we cut down their sample from 128 to 64 because we only look at stars less than 1.2 solar masses, because otherwise, if they're greater than 1.2 solar masses, they have core convection, and that's not really what we're looking at. So we generated a grid of models where we varied the composition and the mixing length of the star, and then we also kind of varied GML more dynamically based on what happens as we vary GML. We might have to vary it more, we might have to vary it less, so that's a little bit more free as we go. But as you can see, we have 10 different mixing lengths and 9 different compositions that we try to match, try to compare the models produced by these parameters to the other stellar observations of temperature and radius. You can see this is our chi-squared formula, and we try and look for models that have the lowest chi-squared and see if there's a relationship between GML and mixing length. That's really what we're looking for. But you might have noticed that the 3 really known parameters for each star are mass, radius, and temperature, but we still don't know composition, age, or GML as a function of mixing length. So we need one more parameter to really nail things down, and that's what we're looking at is surface microturbulent velocity, because it's something we can get from the model, and it's something where we can kind of get from observations, and that's what we're using to kind of constrain the model more. So any questions? Yes. That's the geometric parameter that I talked about. So it's really the surface area to volume ratio of the blob, but it's normalized to that of a sphere, which is 4/9. But yeah, it's just surface area to volume ratio. Yes.
So this material that you get out of the surrounding, is it the same material as its surrounding?
Yeah. Yeah, just the proximate and the outer layers of a star. Yes. We have not run all the models yet, so we have not found anything yet, but we will.
Are you hoping to find something?
Yes, we're hoping to really develop a relationship between that geometric parameter and the mixing line.
That's the observational
there are a couple ways to observationally determine it, but there aren't really any observations of the stars that we're using of the microturbulent velocity of their outer layers, so we kind of have to work with relationships between stellar classification and surface gravity and luminosity and other ways to kind of independently determine what about the range of microturbulent velocity should be based on other properties of the star, and kind of use that to, we don't have enough data to actually put a value to it, but really to constrain our stars a little more. That's it, then I'm going to turn it over to Kevin.
All right. I will be talking to you about a survey that I helped complete the N2H plus molecule toward the Serpens molecular cloud. And I want to thank all of these wonderful organizations for helping. So I'm going to be talking about the motivation why we did this survey, talk about the molecule itself that we looked at, talk about the survey that we completed at the Arizona Radio Observatory 12-meter telescope on Graphite, talk about one of the parameters that we could calculate from our observations, and then give some results and further study. So to start off, I'm going to talk about the beginning of stellar evolution in 30 seconds, showing you this neat little video. Let's see if it's right. So, okay. So, stellar evolution starts out with stars dying. So you start out, have a supernova explosion, and then you deposit all this material into the interstellar medium. Over time, that material gets very diffuse, but it gets very cold. And when you have cold gas in space, it starts to become dense and form molecules. And what you see here is a molecular cloud. And then over time, that molecular cloud starts to get large enough and collapse into protostars. So that's the beginning of a star's life cycle condensed into 30 seconds. So feel free to ask any questions at the end. So the N2H plus molecule, this is what it looks like. It's a linear molecule that rotates. And as it rotates, it has rotational energy transition. So for those of you that know quantum mechanics, we observed the J equals 1 to 0 transition, so the ground state transition of this rotational molecule. So that happens to be observable at the Arizona Radio Observatory 12-meter telescope, and that transition occurs at about 93 gigahertz, so there are some special instruments that allow us to observe that transition. And what we can do is get the spectrum of this molecule, and this is what a typical N2H plus spectrum looks like. Usually there are more than just these three strong emission components. Usually these two parts are split into three further components, and that's called hyperfine splitting, but at the resolution that this telescope can observe at, we can't really see that hyperfine splitting. But that's all due to electromagnetism stuff, such as quantum or quadrupole moments. So, our survey, what we did was we had a paper by Melissa Enoch from 2007, and they completed a 1.1 millimeter dust continuum survey, and this is actually the map that they got of the circummolecular cloud, and they identified 3 filaments in which star formation is occurring, and they identified 35 cores that are either star forming currently or just what we call starless cores. But they did that by comparing their continuum survey to data that they got from Spitzer in the infrared, and that's how they were able to identify these 35 cores. And what we did was we got individual spectra for each of those 35 sources, but we also created what we call on-the-fly maps of each of these 3 clusters identified here. And what that allows us to do is create contour maps of N2H plus abundance in these areas. And we found that this N2H plus is strongest right here, where we overlaid contours over this dust map, and it corresponds very well. So N2H plus must be a very good dense gas tracer. So one of the things that we can calculate from our survey is what we call column density. Column density is the amount of material contained in a unit of area. And that's kind of a hard concept to get your head around at first, but the picture that comes to my mind when I think about this, usually this is like an optical depth simulation, but it pretty much helps explain column density. So you have this column of material, and you're looking pretty much straight on. So you're trying to figure out what amount of material is in this little area that you can see. And some parameters are given to you, such as integrated intensity and optical depth of the telescope, and you can use that to then calculate column density. And this is a histogram of the column density in each of our sources. This is the column density in 10 to the 13 particles per centimeter squared. And as you can see, the protostellar sources have a little bit higher column density on average than the starless cores. Okay. So what we've determined from this survey so far is that N2H Plus is a good dense gas tracer. So like you saw with the contour map, the contours fit very well with the just continuum of gas. So it's a good dense gas tracer. From this plot, you can see that the more massive the core, the more N2H Plus is observed. So you'll see over here on this axis is mass, and this is column density. The higher the column density, typically the higher the mass of the star. And the reason you see that is because the protostellar cores from a Jeans mass calculation are, on average, a lot higher than the mass of these starless cores. And that just means that it has a lot more material. Therefore, the envelope surrounding the core of the star is not yet hot enough to burn off this N2H+. So that's why you're seeing higher N2H+ abundance. Also, protostellar cores are more massive, and you can definitely see that from this plot. And so further study is required to kind of help constrain the stellar evolution. And what we're going to do is compare our notes with another SpaceGrad student, Caitlin Burley and Dr. John Beebe, to see if their study of 12CO and 13CO corresponds with N2H+ to help refine gas phase evolution in protostellar nebulae. Any questions? Yes.
So that abundance map, the initial it looked like what wavelength of light is the underlying map?
So this underlying map is 1.1 millimeter dust continuum survey. So that's our survey of N2H Plus is at about 3.3 millimeters. So so we overlay the 1.1 millimeter dust continuum, which is also in the radio. We overlay our plots with that continuum, and we see that N2H Plus corresponds very well with just continuum dust. Yes?
How do you make that contact?
There's a special program in the data reduction package for the radio software called Class, or it's either Class or Greg, I can't remember. One of the two, but yeah, the contours are easily plotted if you have on-the-fly maps of spectra. Yeah, and if people know radio astronomy, which I don't expect anybody but Camber to know, these contours are 3 sigma contours, which is like a standard for radio. You want like 3 sigma contours. This one, to show any structure, are only 2 sigma, so but you can see that this, people don't even call this cluster C because there might be one star core in that filament. But it's a lot harder to really see any good structure in there at the areas. And so I'll show you, this is the actual equation for column density, and it's really not as terrible as it looks, because everything on this side of the integral is pretty much very well known parameters based on, like, if you have the wavelength that you're looking in. All of this stuff is easily looked up, or you can put into smaller equations that aren't that scary. And we get the integrated intensity and the optical depth from our observations. So it's really not that scary of an equation. It just looks big and scary because it's long and it's equations within equations, and you have to know a bit about quantum mechanics to fully understand this equation. Yeah.
How do you get optical depth from your observations?
Magic. I think it's one of the given information that the yeah. That's good wavelength. This slide kind of shows gas phase evolution. and how you get N2H plus. So most of molecular clouds consist of H2, so H2 regions. If a cosmic ray happens to hit H2, it'll ionize it, and we've got some ionized H2 that might combine with another hydrogen to make H3. Also, you've got a very little abundance of molecular nitrogen floating around, and it's very possible that this nitrogen will combine with this ionized hydrogen to create N2H plus. And then the further step in this gas evolution is that the CO, which is much more likely to be in these gas clouds, will combine or try to strip off this hydrogen, so then you get HCO plus. And it's kind of confusing. If you don't have as much CO in this cloud, then our N2H plus molecule will form, and over time it's more likely that this H will just want to go back into space and not really want to be with this N2 guy over here. That's only if there's much less CO in this gas. Huh? Hundreds of thousands of years.
Wouldn't that give you a time for have a lot of it?
Yeah. One other cool thing to put into perspective, this is density of things in space. So the vacuum of space is pretty much defined as 1 particle per cubic centimeter. So just imagine in this room, if we had 1 particle per cubic centimeter, that'd be really weird. For cores to start collapsing, or for a protostar to collapse, you need about 10,000 to a million particles. For the core, you need about 10,000, but for an entire protostar to start to collapse, you need about 1 million particles per cubic centimeter. But in this room, it's really weird to think about. We have 10 to the 19th particles per centimeter cubed. So stars, they really form in not very dense areas of space. And it's very cold. That's how H2 comes about in these cold, dense, relatively dense regions of space. So I think that's always kind of neat to just put that into perspective, that you're breathing air that's 10 to the 19th particles per cubic centimeter, yet stars form in about 1 million particles per cubic centimeter. So I always thought that was cool. But those were my additional slides that are really part of the presentation. Any questions?